language models, but today Mark and Warren are going to talk about how small language models are actually their powerful tool to match freelancers and companies. Mark is the director of data science at Malt, and Warren is leading the R&D for advanced matching topics. So please give a warm round of applause for Mark and Warren.
Yeah, thank you for the introduction, and hi everyone. So I'm Mark, and with my colleague Warren here, we're super excited to be here today to talk to you about how we scale freelancer matching at Malt, thanks to a small language model that is a bit special. So first, a few words about Malt, because you might not all know the platform. So we're the freelancing marketplace leader in Europe with more than 700,000 freelancers. And we make the perfect match happen between freelancers and company. So as you might have guessed, making that perfect match is a big focus of the data science team. And as a company, you have two main ways of finding your talent. The first one is through a search. You can browse the profile, select the one you're interested in, and contact them. The second way is by describing completely your project. And then our recommender system is going to take care of contacting the best freelancer for you. So for today, we're going to focus on that recommender system. We had a recommender system in place for a while. At its core, we find the ranker, which is basically in charge of seeing how good the fit is between a freelancer and a project to, in the end, come up with a ranking. The problem with that approach is that it can take a long time. When you think about it, if you want to have the global ranking, and if you put aside the filtering that you can apply at the beginning, you might have to call your model up to 700,000 times to get the score for each pair of project and the freelancers to get the global ranking. So a usual way to deal with that is to add a retrieval phase, also known as candidate generation. And in our case, it means finding a way to go fast, but of course approximatively from 700 freelancers to a few hundred good candidates. Once you have these candidates, you're back to normal and you can send them to the ranker. So that looks great, but Warren, So for today, we're going to focus, of course, on how we build that retrieval. That looks good, but Warren, how could we build such a retriever?
OK, so before jumping to a solution, what we can do is we have a look at what data we have at disposal. So whenever a company contacts us to do automatic matching, we ask them to fill in a brief, and this brief contains three types of information. So the first one regarding what kind of freelancer they are looking for. So a job title, we ask them also to select a job category from our taxonomy, and then some mandatory and bonus skills that the freelancer should have. Then we ask them some business information, how much they are willing to pay, when should the project start, how long should it be, and finally we ask them to describe what will be the mission with a mission title and a mission description. On the other hand, the freelancers have profiles on our platform. This profile contains information about themselves, so with a job title, a job category also, some skills that they possess, but also a description about who they are and what they can do, and some past experiences. So with those two documents, we could do a perfect word match, meaning that we will retrieve the profiles that contains most of the keyword from the project brief. And in short, that is lexical matching using BEM25. So that sounds great. It sounds actually perfect. But did we solve retrieval with BEM25? Not really, because otherwise we wouldn't be here doing this presentation. So BEM25 is quite fast. But lexical matching doesn't grasp the meaning and the context behind words. And these, in our case, have some issues because freelancers and companies may not speak the same language and may not use the same dialect. They may mean the same thing, but not express it the same way. So some example, a company may actually deem important to mention Git as a skill, whereas a developer, it's actually obvious and they don't even mention it on their profile. Another example is maybe a company is looking for someone that can do deep learning, but for a freelancer, they may rather choose to define what kind of technologies or what kind of framework they are using. And lastly, what we would also like to do is to be able to match freelancers and companies, even though they are not using the same language in their profile and their briefs. So we could actually keep BM25 and tackle all of those issues separately, but Mark, is there a magical solution that can tackle all of those issues at the same time?
Yeah, of course, Warren. So generative AI. No, I'm kidding. Neural retrieval. So let's take a look at what is exactly neural retrieval. To build a neural retriever, you need an organized latent space. So what is a latent space? That's where the embeddings lives. And what are the embeddings? It's basically the coordinates for our profile and our project. Here we've got an example projected in 2D, and we see some kind of organization with one job category being in one part of the space and another family in one part of the space. That organization, in our case, would mean that the distance equal the skill match level. So if two freelancers or a project and the freelancers are next to each other, there's a good skill match. If they're far away, it's a bad skill match. To get that latent space, we will need encoders. So since profile differ a bit from the project briefs, we will need 2 encoders. But if we manage to get these encoders, then it's fairly easy to do the retrieval. Because when we get a new project, we just have to encode that project and get its embedding, so basically its coordinate. And then we just have to look around. Who are the closest freelancers? So here, the nearest would be the best matches that we would send to the ranking phase after. So that looks good, but how do we get these encoders?
OK, so since we're working with text, we can actually have a look at the language model landscape. So a bit of a side note, this figure is actually outdated. As we all know, things are moving quite fast with language models. But this figure is still interesting because you can see that depending on the model, they may have different weaknesses and strengths. And if we zoom a bit back and look at how they are trained, we see a pattern emerging. And when a model is trained in auto-regression, meaning that it's just next word prediction, seeing only what is before this word, they're actually better for content generation. Whereas when models are trained using auto-encoding, seeing the full sequence, they're actually better for extracting information. So in our case, we don't want to use GenAI models. We actually want to use encoder models. But if you recall what I said earlier, we have another constraint, which is that we want cross-lingual matching. And so the big question is, how do we do cross-lingual matching?
OK, so the answer is that multilingual language model is probably what we need. Because there's 2 properties in these languages that are interesting for us. The first one, and I already talked about it, is that the latent space is going to be organized. So similar things should be close to each other, and things that are different should be far away from each other. But the other constraint in multilingual language model that we want is to have the alignment between the language. What alignment means is that for the same concept in different languages, we should have roughly, they should be roughly located in the same location in the latent space. But we should be careful, because not all latent space are born equal. Depending on how you train your model, you might get these nice properties, or you might not. So you need to carefully pick which multilingual language model you want. A good candidate for us is to take a look at the multilingual sentence bird for two reasons. The first one is they are trained on sentence similarity, so that's what we'll get for the nice organization in one language. And then they have the language alignment through distillation. So now we at that, we could say, OK, we have a model. It's aligned between the languages. It's organized. So we could use it as is. The problem is that if you remember at the beginning, we want the distance to represent the skill fit. But it was trained on sentence similarity. So the distance is more about semantics. So it's not exactly what we want. So then you could say, OK, let's fine-tune these models on our data. The problem that you're going to do now, what's going to happen is that you're going to break the alignment between the language. So for example, at Malt, we're a lot in France, Germany, and Spain. So these countries and the languages they used might actually favor this language and break the generalization in other languages. And in addition, in both cases, as you remember, Warren presented, like we have some structure in the profiles and the project brief. But here, we're just like aggregating everything and losing the section and the structure. So now the next question is, how can we adapt to our use case this pre-trained model while keeping the interesting properties I just mentioned?
OK, so to build this in-between solution, what we decided to do is to create and develop our own architecture that is able to process documents, so briefs or profiles, into a unique embedding vector. And the big picture is that this architecture is made of 4 steps, 2 which are submodels, and 2 which are formatting steps. So the first submodel is actually a multilingual model that we use as a frozen backbone to keep the language alignment. And the second one is a trainable head based on a BERT model that will be trained to fit and adapt to our skill matching case. So that is for the big picture. Now we can deep dive a bit into each of those steps. And so for the first step, we need to decide how we can model documents. So here you have Jouanneau's profile, as an example. And you can see that there's different sections into it. What we could do is just concatenate all the sections into one text, but we will be losing the structure of the document. So what we could do in order to keep the structure is to separate each section with a special keyword. But in both those cases, what we saw in our experimentation is that we introduced too much noise, giving to a model all this text at once. It's actually not the best way to do it. What we could do, however, is to use a larger model and more data, but that is not the path that we decided to follow. What we actually did was to process each section independently. So first obtaining sequences of token IDs, and then processing those token IDs into the same backbone, we obtain one sequence of token embeddings per section. So after this first step, just before the second step, what we have is multiple sequences of tokens embedding, where each token embedding contains the semantic content, which is language aligned, because we keep the backbone frozen, but also it contains a bit of information about the position of the token in the sequence, and also, due to the attention mechanism, some of the section context. But we are processing sections at that point, and what we want to do at the end is process documents. So we could do a simple concatenation of all those sections, but we will be losing one information. The information that we will be losing is the section of origin of each token. So what we did for that is we just added some section encoding. For those who are familiar with it, it's a bit like positional encoding, but instead of encoding the position in the sequence, we encode the section in the documents. OK, so now we're getting happier and happier about it. We have a unique sequence, and we are not losing the section of origin, but we are still talking about semantic content. To move from the semantic world to our specific skill matching world, we need to train a head, and we also use a skip connection. The skip connection is a well-known method to simplify training. And in our case, since we are keeping the backbone frozen, you can see it as the head is actually learning what is the difference between the output of the backbone and our specific domain. And each of the tokens also contain a bit of the document context due to the attention mechanism. So now there is one last thing that we need to do. We need to move from sequence to a unique embedding. Well, we can just do a pooling. We can just use a pooling operator. Often we use the average pooling, but in our case, it's not well suited because the description contains much more tokens than all other sections. So if we will use the average pooling, we will just the final resulting embedding will contain mostly description contents, and it wouldn't be balanced. So what we do instead is we use a weighted sum pooling by normalizing by the number of tokens in each section. OK, so that sounds great. We have a unique embedding per document. This embedding contains skill matching content while preserving language alignments. And if we zoom a bit back, we managed to keep things small with this architecture. We have actually only 113 million parameters for the backbone, which is frozen. And since the backbone is frozen, we are keeping the language alignments. And we have 7 million parameters for the trainable head. So we have only 7 million parameters to train, but the big question is, how do we train those parameters?
OK, so usually to train such model, people rely on contrastive loss. In contrastive loss, what they do is they exploit the relationship between data points to organize the latent space. So here you've got an example with a project brief and a positive match for it and a negative match. So what we would do is just pass this freeze entity through the model, get their embeddings, and now the goal of the loss is going to be to push away the negative freelancers from the location of the project and bring closer the positive freelancers. So the good news is that we do have historical data at Malt from which we can derive this relationship. So when a freelancer receives a project, they can say that they are interested in that project, or they can refuse the project and decline by selecting a refusal reason. One of these refusal reasons is that they do not possess the skill. Likewise, the client can say the same thing on freelancers that are interested. They can say, I don't think that this freelancer has the right skill. So overall, we can use this feedback as a proxy for the skill matching. If everyone is interested, we consider that as a good skill match. If there's one of the party that has a doubt, then we consider that is a bad match. However, there's also a bad news, which is that that data is not perfect for two main reasons. The first one is the quality, because both freelancers and company might not select the right refusal reason because they did not understand the implication. They fear also what is going to happen. So we cannot trust fully these feedbacks. The second problem is that we've got a huge presentation bias, because the freelancers that say that they don't have the skills were actually proposed by the recommender system. So the system thought it was a good candidate. So when you think about it in the latent space, they shouldn't be too much far away from each other, because it initially thought it was a good fit. So is there something we can do about it? If we take a step back and see if there's other data that we could exploit, our job taxonomy is a good candidate. Because on Malt, sorry, not the same platform, when you create your profile, you can select several job categories. to define what you do, and the same for the companies when you create a project. So it's a reasonable assumption to say that if they have non-job categories in common, it's a bad match. But it's only something we can use for the negative match. Because for the positive, being in the same category, I mean, having one category in common is definitely not enough to say that it would be a good match. That's great. We can augment our historical data with this synthetic negative interaction. It's great for two main reasons. The first one is that we can pretty much control like how much negative we want. The second is that these negatives are like weaker, easier to learn for the model, and they are going to be pretty useful at the beginning of the training to structure the latent space. I've talked about the data, but we still need a loss. So one of the most popular loss in contrastive training is the triplet loss, which is initially coming from the computer vision for face detection. It's pretty similar to actually the example I gave. So it's a triplet, and as the name suggests, you need 3 elements. So here we've got our anchor, which is a project, and you're trying to push away the negative match and bring closer the positive one. So that loss works relatively well, but then it brings a lot of questions, such as like, how do you pick the triplet? How do you find the best negative? So that's why more and more people are moving to enuplate type of losses. And for us, it's a really good fit because we can exploit the historical data I showed us, but also we can mine within the batch weaker negative based on the job taxonomy. So just to give you an intuition, I won't dive into the loss in detail, but you could see that as a multi-class classification because you've got a kind of a cross-entropy term on the left. It's just that instead of the logit, you've got the dot product of the embeddings. So that's great. We've got an architecture, we've got the data, we've got the loss. Unfortunately, we won't have the time today to cover the detailed evaluation, offline evaluation that we conducted. If you want more detail, you can take a look at the corresponding research paper. I'll put a QR code at the end. But to give you an intuition about, to know like if that approach is actually working, we're showing you here a density plot of the freelancers that are colored by their job family. What you can see is, so I don't know if you're familiar with this kind of plots, but basically like the darker it gets, it's like a density bump. So you can read that like a map. And you can spot sometimes that you have like several bumps into a job family. And actually, if we zoom in one of the job families, so here that would be the web graphic design family, we see that these bumps are actually categories in our job taxonomy. I guess you can still see that we still have bumps in these several bumps in like a given job category. We didn't have time to investigate, but we think that we probably have like kind of subcategories within our categories. OK, so now we have trained these encoders. You've seen the result, not the offline evaluation, but at least the latent space. How do we use them in production, Warren?
OK, so to use them in production, to use those encoders in production, what we need to have is a database to store the profiles embeddings. So for 3 reasons, of course, store our existing profiles, but also any new profiles that will come from a new registration on the platform. And lastly, we also need to schedule some routines to take any changes of the profiles into account. And we need to store those embeddings, those profile embeddings, so that whenever we receive a brief, we can look in this database for the nearest and the closest freelancers. To do that, we could use KNN, so k-nearest neighbors. However, for production, it's quite slow. So what we use instead is approximate nearest neighbors, which is actually way better in our case in production, as it's way faster. So what will be great if our database could at the same time store the embeddings and perform this ANN. There's a great news. This solution exists, actually. It's called a vector database. And vector databases are not new, but we have seen a rise in popularity due to the hype in GenAI, and mainly and especially with the RAG pattern. So there exist multiple different vector databases. And at Malt, the MLOps team conducted an analysis to select the best fitting one. And you can find the analysis on our engineering blog. But the conclusion was to use quadrants, as quadrants offers a good balance between latency and the precision, while also enabling us to have additional filters, for example, geospatial filters. And moreover, what is great is that those filters are applied at the same time as the vector retrieval is done. So this has a great impact on latency and the quality of the results. So we've worked to have small models with our architecture. We also conducted an analysis to select the best suited vector DB for us. But is there any last thing that we could do on those encoders, Mark?
Yes, so let's take a look. So yeah, ideally, we'd like to deploy everything on CPU. So is there a way to make our model fast enough so we can run them on CPU? So the answer, one answer is inference runtimes. So these are, as the name suggests, dedicated runtimes for inference. Usually they are written in lower level languages such as C or C++, but they do offer API to Python. Usually they bring several family of optimization. Right now we will just cover the two families of optimization we actually used for that specific model. So the first family is graph optimization. So we frequently represent a deep learning model as a computational graph. And what basically graph optimization is going to do is rewrite that graph to make it simpler while preserving the same output. So here on the right, you've got an example with a node fusion, where like 2 steps of the model are going to be fused in one operation on the CPU or the GPU. So you've got basic rewrite operation, and you've got more advanced optimization that are either specific to some hardware architecture or like neural net architectures. OK, the second thing that we did is quantization. So now it's getting more popular because the big LLMs are like unusable otherwise. And quantization is about mapping the parameters of the model into a lower precision representation. So usually integers, 8-bit integers, or even sometimes lower for the biggest language model. One of the reasons quantization is great is that it's not just the mapping, because we know that empirically the distribution of parameters in a model follow a Gaussian distribution. And to lose very few precision, what we can do is just cut the tail of that distribution and just do the discretization on the mass of the distribution. So thanks to that, we're going to keep most of the precision. So if we take a look at the result in our use case, so this is on CPU, we managed to almost reduce the execution time by 3. And it brings to, 17 milliseconds is like usable in production for the use cases that we have. And we also see that we had a huge gain on the model size, which was divided by 4. So that's on like increasing the inference performance. But what about the precision? If you look at the bottom, we check that by comparing the cosine similarities between Onyx and PyTorch, and we see that the differences are really small. And to be honest, the approximation introduced by the ANN is going to be like way higher than the approximation we are introducing here. OK, that looks really shiny. I'm sure you want to do the same thing at home, but does it actually work in the real world?
Well, here we display the latency evolution of our API. And what you can see is that we went from tens of seconds to a maximum of 3 seconds when we introduced the neural retriever. What you can also see is that we mentioned an A/B test. So I'm sure you want to know what was the conclusion of these A/B tests. Well, we actually managed to improve conversion. We were not expecting that. Our goal actually was to not degrade conversion, as we did not do any changes on the ranking phase. But the way we explain it is that due to the new technology that we are using with the neural retriever is actually able to remove some suboptimal candidates that were highly ranked before. So our goal was to reduce latency. That's done. We actually went further than that by also increasing the conversion. Is that the end of this project, Mark?
Yeah, I think everyone wants to have lunch, so I think we can stop here. No, I still need 2 minutes. Actually, if you remember, today we focused on the automatic matching part, which is project-based, where we actually want to bring back all that we've built on that product to the other one, which has a query as input. But there are some cases where neural retriever that's not the best solution, especially when you have like smaller inputs. So another topic that we're investigating right now is hybrid retrieval, where you actually combine the lexical retrieval that we presented first and the neural that we explained in detail today. So to conclude, this project was a team effort, so I'd like to thank all the team. So everyone is distributed in Europe. Not everyone is here today. And as a reminder, if you want more technical detail, that's the QR code of my Bitcoin wallet, the research paper. So yeah, do not hesitate to take a look, and we're available for questions.